Now let's take a look at quadratic functions. So we can start off by looking at what we've already seen with one of our parent functions, namely the squaring function. So here we have a function, and we know its parent is y equals x squared. Let's talk about what is being done in these series of transformations. So before we square, what do? We're subtracting 3. So that means that it's going to be moved right 3 units. And then secondly, notice we have a negative 1/2. There are two things that are going to happen there. It's going to be a reflection about, now it's the outputs that are changing, so that will move it across the x-axis because the y values change. And at the same time, we have a vertical compression by a factor of 1/2. And then lastly, we have a movement up 5 units. So let's graph that. Remember our 3 key points to begin with yield this shape. So let's go ahead and move right 3. So I'm going to focus in on this point 0, 0. We're going to move it right 3, then reflect it, compress it, and then move it up 5. So we'll end up being at 3, 5. Negative 1, 1, moved right 3, 1, 2, 3, reflected, and then move up. Compress it by a factor of 1/2, and then move that up 5 units. So 1, 2, 3, 4, 5. So we're looking at about 4.5. Not about, it is 4.5. And then likewise, we move the point 1, 1, and we get this. So our answer looks like this. So what we see here is what's called a parabola. So this is also a quadratic function. So a quadratic function is any form or any function of the form ax squared plus bx plus c, where a, b, and c are real and a is not 0. So in other words, we have to have that squared term for it to be a quadratic function. And the shape of the graph is called a parabola. Now every parabola has certain key characteristics. The vertex, and that vertex is either at the bottom or the top of the parabola. The axis of symmetry, which is the line that crosses through the vertex. It also cuts our parabola in half so that it's symmetric on either side. And you'll notice that sometimes we have a parabola that opens upward, it's cupped upward, it's concave up. And if it's concave down, it's cupped downward, it's opening downward. And if it's concave up, we have a minimum value. The minimum value corresponds to the vertex, and it's the y value of the vertex. Likewise, if our parabola opens downward, then our vertex is at the top, and its y value corresponds to a maximum. Now, if we have a quadratic function, we can always write that quadratic function in vertex form. So this allows us to think through it in terms of our transformation of functions. And even more so, our vertex can always be seen by what's being subtracted from the x value. So x minus h will be the x value of our vertex, and then our shift for k will correspond to the y value of our vertex. Our axis of symmetry, since it always passes through our vertex, will always be x equals the h value of our vertex. And then if our parabola is opening upward, it's because a is positive. If our parabola is opening downward, it's because a is negative. So let's take a look at an example. So first thing that we're going to do is we're going to identify a, h, and k. So a is the coefficient 2, and we're subtracting 3 from x, so h is 3, and k is negative 5. So our vertex is 3, negative 5. Our axis of symmetry is x equals 3, and a is positive. So since it's positive, it's concave upward. Now, let's go ahead and plot the point that corresponds to our vertex. So 3, negative 5. It's opening upward, and you'll notice that we've stretched it by a factor of 2. So that means instead of having our typical points here and here, we'll stretch those by a factor of 2. So they will be here, away from our vertex. So now we can go ahead and graph. So it's going to be a very tall parabola. And you can tell what your axis of symmetry is because it is going through your vertex. So notice x equals 3 is your axis of symmetry.